Hello, everyone. Welcome to the session. Hello, Professor. How are you
Hello.
doing? Okay. So we have Dr. Tattvamasi Amrutam here. First of all, I would like to introduce him about everyone. So Dr. Tattvamasi earned a bachelor's degree in mathematics and computer science from IMA, Bhubaneswar, back in 2014, followed by a master's in mathematics from IIT Bombay in 2016. He has completed his PhD in mathematics at the University of Austin in 2021 under the supervision of Dr. Mehtarat Kalantar from 2021 to 2024, if I'm not mistaken. Correct me if I'm wrong, sir. He was a postdoctoral researcher at Ben Gurion University of the Negev, working with Dr. Ya Hatun. He is currently an adjunct assistant professor at the Institute of Mathematics, Polish Academy of Sciences. Right. So without wasting any time, let's begin the session. Sir, over to you.
Thank you, Sudip, for the introduction, and thank you for the invitation. So I'll try to give a very, very fast introduction to what these objects are and try to motivate them and give some examples of C algebras that naturally occur, or the people the objects that people work with. Okay, so to start out with, the world that we know of or familiar with is the finite world. For example, we have the matrices. So the matrices are finite dimensional objects. They work on the finite dimensional Hilbert spaces, for example, Rn or Cn. And then this is the world. And how do we see them? So the way we see them is via their actions. For example, translation. Right? You can translate a vector along certain direction. You can rotate it, or you can reflect. And everything that we do in the matrix, in the finite dimensional world, can be written as a finite combination of all of these three guys. So everything else is basically covered by them. And one of the important facet of these matrices is the central equation that governs them is the equation of the eigenvalues, AV equal to lambda V. And these eigenvalues, this can be thought of as fingerprints for matrices. So basically, all the information that we want about matrices, we can really find them out by knowing all the eigenvalues in many, many examples that we work with in the real world. But what if the world that we work in is not finite? What if it is infinite? And many systems in the real world, for example, quantum systems or signal processing units, these are infinite. These requires more than finite things. And here, what we deal with, what the matrices, the analog thing for them should be infinite matrices, or what the term that people use for these guys, these are called operators. So the matrices that we worked out in the finite dimensional case must now be replaced by infinite dimensional matrices, and these what we call operators. Now, but what is the playground for this? Like, because in the matrix case, we knew that the playground was these finite dimensional objects like Rn or Cn. But what is the stage that on which these operators are acting? And this is called a Hilbert space. So this is the stage on which these operators act. But the one key aspect of working with these infinite matrices is that they may not have any eigenvalues to start out with. So then the fingerprints that existed for the finite dimensional matrices no longer exist. So then how do we determine what these operators are? And then the right objective, as we shall see in our course once we go there, is to look at what we call the spectrum associated with an operator. And then from this spectrum, we can necessarily determine what these operators are and so on. So now, once we know that there are these infinite dimensional matrices or operators, and our stage is the Hilbert space. Now, Hilbert space is an infinite dimensional space where geometry still works. So everything that we knew for the Rn or Cn, that we can still do. So this is an example of, I try to draw, but it's not actually there. But we still have a solid notion of length of an angle and a notion of distance. So all these things that made sense for the finite dimensional Rn or Cn still make sense for this generalized Hilbert space. And this is exactly the stage that these operators work with. In the very end of this lecture, the C algebras that we are going to work with are not very far apart from these operators acting on these states of Hilbert space. Okay, so let me now pivot a bit and give an example of a C-star algebra that people work with. So most of us here are well versed with the notion of a group, right? So G for me is a countable group. I'll give an example in a bit. So there is this operation of whatever operation, the group operation is there. And now I have a unitary representation. Think of it as a homomorphism from group G, and this is the collection of all unitary operators. So let me call them as unitary infinite dimensional matrices. So it's very much similar to the unitary operators that are there on Rn or C in the whatever orthogonal group that you know of. So now I have the homomorphism from the group to this unitary, the collection of these unitary infinite dimensional matrices. And one of the key properties of this is that it preserves the group operation. So pi zh is pi g pi h. This is the property that I enforce on it. Now out of this, I'm going to create this group C-star algebra. This is the first time I mention this word. I have not defined it yet, but bear with me. So what I do is first I look at the span of these guys as G varies over the G, and I close it in the norm. Now, of course, the span, like if it is a finite dimensional representation, then the span is going to cover everything and there is no problem. But since I'm working with an infinite dimensional object, I must close it to make it a very nice object. And whatever object that we got here, that is called the group C-star algebra associated with this representation pi. So of course, as pi varies, I get a very different collection of these C-star algebras and so on. So a priori, even though the group did not have any notion of length or measurement or anything, but now suddenly by doing this thing, we get a notion of a length, a measurement associated with it. Okay, so now let me give an example of a very special unitary representation, which we call the left regular one. Now, what is the left regular one? So first what I do is I enumerate the group elements by delta G. So I am thinking of each delta G as a function from my group to C. Now, what am I doing with it? If you give me an element H, I send it to 0 if G is not H and 1 if G is H. So it's a Dirac function at the point G. So these are my functions. So this forms an orthonormal basis. If you're familiar with linear algebra, then this is an orthonormal basis for this infinite dimensional Hilbert space. Now, what I want to do is, so lambda is my representation. That is the usual notation for the left regular one. This must be mapped into the unitary operators on L2 of G, right, based on my notation. So what this means is that for each G or H, I must tell you how does lambda H act on L2G. So this must be a map from L2G to L2G. That's how. And since we know this from before that matrices, in order to define matrices, we must tell what happens to the orthonormal elements in the orthonormal basis. And that's exactly what I'm doing. We need to tell what happens to the orthonormal elements. So I need to tell you what happens to delta Z. Where should this map be? So basically what I do is I just translate them, delta HG. And that's exactly what is happening here in this map. So I just take each orthonormal basis element and I just keep on translating them by each group element, depending where it is sent. And then this defines a very well-defined map. And then the process that we just described in the last slide, this will give us the reduced group C-star algebra. So this is the span of these lambda Z's. And then I close it in the norm in B of L2Z. And this is what we call the reduced group C-star algebra. Okay, so before we move further, let me just put this out. So Alan Kohns, who is a Fields medalist and still works in operator algebras, he posed these questions as conjectures, which are yet to be solved. So his question was the following. So take any two different groups and do the same procedure that we did. Suman is asking if I can explain the previous slide. Okay, so here what I'm doing is that I'm trying to define a very particular case of an unitary representation, which is called the left regular. So what I want, like I said here, I want to define a map, a homomorphism from group to the unitary operators on L2Z. And to do that, for each H in a group element, I must define a map. So lambda H must be mapped from the Hilbert space to the Hilbert space. So this is my Hilbert space here, H. And if you know linear algebra, then in order to define a linear map between any two Hilbert spaces, or if you think of Rn, it is enough to define it on orthonormal elements, right? If you just define what happens to each orthonormal element, then it extends linearly and continuously and so on. And that's exactly what I'm doing here. So since these are the orthonormal elements, I need to define them individually on each of these guys. Now what I do is I just translate them to some other orthonormal element by H. So this is the group operation. Here there is the group operation. I'll come back to a very concrete example of integers in a moment, but this is exactly what I'm doing. And then the same procedure that I do, I just take a very like a span of these guys, finite linear combination, I close them up in the norm, and then what I get here is the reduced group C-star algebra. Okay, coming back to Alan Kohns, he posed the following question. So the question is very general, but I just kept it in the original form that he posed it in. That if you take two different groups, think of any of your two favorite groups that you know of, and do the same, like think of these as functors, the C lambda star. So this is a functor. Can this functor differentiate between two groups? That is his question. So in particular, he asked the following question. Take SLNG and SLMG, the determinant 1 matrices, n-dimensional and m-dimensional over integers. Then apply the same functor that we just did, this C lambda star functor, and assume that these guys are isomorphic as C-star algebras. In the category of C-star algebras. Does this imply that M must be equal to M? Of course, if N is M, then one direction is straightforward. But the other direction is very difficult, and it is still open for Nm bigger than or equal to 3. And similarly, he asked for the von Neumann algebras, which I have not defined yet, but this is also constructed very similarly. Let me put it out here. And closed in a weak operator, in weaker topology. We'll get there once we study these things in detail. So this is, as you can see, these are very interesting objects. People have been thinking about these problems for a long time, and they remain unresolved for the time being. Okay, so like I promised, I want to talk about the integers for a bit. So the group G equal to integers is very well known under addition and so on. As you can see, I have enumerated the orthonormal basis by the group elements 0, 1, 2, -1, -2, and so on. Now, so what I want to do is I want to define lambda 1, let's say. So lambda 1 must be a map from L2Z to L2Z. So in order to do that, I must tell you what happens to each orthonormal elements. And like the figure says, what it does is that it just sends delta 0 to delta 1, just translating it by 1. It takes 1 to 2, 2 to 3, and so on, -1 to 0, -2 to -1. So in general, what it does is that if you take lambda 1 and you apply to any basis element delta m, it just takes it to delta m plus 1. You just translate it. And in general, if I look at any k, I just shift it to delta k plus m, and here I'm of course doing delta m plus 1. So in particular, each lambda k gives me a map from L2Z to L2Z. All right, and it is defined exactly like this. It just keeps on shifting these orthonormal bases. And then I just do the same procedure that we did from before. So what we do? We take G equal to Z, and then we apply the functor, the C lambda star functor, and that we get is that C lambda star G, right? So how is this defined formally? This is the span of these lambda k's as k varies over the integers. And I close it in the norm. Right. So this is the C lambda star functor, or the machinery that we just described. Okay. So now as you can see on the figure, I have drawn the circle S1, and there is a connection between these two objects. It turns out that this object that we just created, this guy is isomorphic as a C-star algebra to all continuous functions on the circle. This can be shown by a Fourier transformation. Of course, we don't have the tool. I mean, we do not know all the tools for this moment. You have to take my word for it. And this is all the continuous functions on the circle. And so on. depending on the group, and then if we apply the functor, we get very, very different objects, and the group structure determine this object. So just to point out here, G is abelian group, right? So the commutativity is preserved. And that is an important fact that we'll come back to later at some point in time. Okay, so now based on these examples, just to wrap it up, so what we have is that there are two different worlds, but one set of rules, right? So the first world was very non-commutative, right? Like infinite matrices. So think of MNC, for example, or if we are very brave, like these infinite dimensional operators, right? In MNC, for example, two matrices do not necessarily commute. So this is this world, right? This is analytical. So this is analytical, the infinite dimensional matrices BH, and moreover, these are non-commutative. So abstractly, this is one type of world that we are working on. And in the second world, there is this notion of the continuous functions on the circle, right? Continuous functions somewhere on some compact Holzer space. If you know a bit of topology, then this should make sense for you. Or think of, for example, the closed interval 0, 1. In this world, everything commutes. So everything commutes. And this is topological in nature. And an example is like we saw the continuous functions on the circle. Right? If you take two functions and you multiply them pointwise, they commute in this sense. Now there are two different worlds. These are two different C-star algebras. But how is the connection made? So the C-star algebra is the one framework which puts them into perspective. So any system that follows these rules, we have not defined them. There are three different fundamental rules, which I'll describe them in detail. But any system that obeys these fundamental rules is called a C-star algebra. And then all of this is going to be put together in the course when you do that in one climax. And the climax is one for the commutative version, which basically says that if you take a commutative unital C-star algebra, no matter what they are going to be identified as continuous functions on some compact Holzer space X, like we saw. C lambda star G. This was isomorphic to the continuous functions on the circle. And the key point, like I mentioned, was that this is an abelian group. So this was commutative. So therefore, it was a continuous function on some space. And this is not some fluke. This is one of the famous theorem of Gelfand and Naimark that says that if you take unital C-star algebra which is commutative, then it must be continuous function on some space somewhere, and that's it. So this is the formal isomorphism. We have an abstract commutative C-star algebra on the left-hand side, and on the right-hand side, I have this concrete topological object, continuous functions on some space. And the final one, the GNS, the Gelfand-Naimark theorem version 2, says the following: that every C-star algebra, no matter what, no matter how abstract, it doesn't matter, this can be realized as some infinite dimensional matrix on some Hilbert space H. This is the final theorem that we shall prove in our course towards the very end. So abstractly, we know where to find C-star algebras. We can just look at some operators on some infinite dimensional matrix and some operators on some infinite dimensional Hilbert space, and then this should give us C-star algebra very, very abstract. And this is the key point in the C-star algebras theories. Now, coming back to the course. So what we shall do, this is a 2-week, weeks 1 to 3, what we're going to do is we are going to talk about the stage, the Hilbert space, then the bounded operators, these are the actors. The language is going to the spectrum, like I said in the beginning. These are the fingerprints that we shall work with. And then finally, in the second week, we shall come to the abstract C-star algebras, the rules, the Gelfand-Naimark theorems, and we shall finish it off there. And then finally, we'll have 3 options to do a project. One is to look at the von Neumann algebras. I didn't go into that, but the von Neumann algebras can be thinking about the major theories idea of operators. We have to introduce some sort of a measure there. We can also do tensor products. So tensor products are very, very useful in quantum information theory. So in here, we shall know how to combine 2 different C-star algebras into one object and study them. And the third thing that we can do is to look at K-theory of C-star algebras and seeing. So this is this widely known program of Kunz and Elliott is to distinguish two different C-star algebras by their K theory, and we shall see how we can do that. These are all the possible projects that we can explore in this course. And that's where I'll stop, and then I'll leave you open for questions.
All right. So if anybody is having any question, please raise your hand. There is a hand raising tool. Yeah, Jayaditya, go ahead, please.
Thank you so much, sir, for the talk. What I wanted to ask you was, what would be the prerequisites needed for a course? Because from what I saw, it was quite an advanced lecture.
So the prerequisites should be linear algebra, I would say, and some sort of familiarity with real analysis. I think those are the two things that you should have.
Yeah. Thank you so much, sir.
Yeah, Virupaksha, go ahead, please.
Thank you so much, sir. So for the real analysis part, can you please specify what we should read? Because I have done a bit linear algebra, but I don't know much about real analysis yet.
So real analysis, I would assume, like for example, if you have Rudin, then maybe the first 4 chapters should suffice. Like sequences, series, continuity, and differentiability. I think this should be enough.
Okay, sir. Thank you, sir.
Okay, Monica, I think you were writing something. Can you please speak up? What is your query? You want to see the recording? Okay, fine. That will post. Then you can check it. Okay, any other questions? Anyone? Yeah, Suman Chakravarti, go ahead, please.
Sir, in the beginning, you were saying that that set of all unitary operators on that Hilbert space, and you are taking the image. I mean, from the group, you are defining the map G2 set of all unitary operators, and then you are taking the closure, right? So my question is, what is the norm there? I mean,
The
to
norm
take a
is the
closure,
norm.
you need a metric first of all.
Sorry.
I mean, to take my closure, we need a metric or any norm. I mean, if there is a norm, there is a metric. So what is the norm?
There is a norm on B of H, so I'm just taking the closure in that norm.
Okay. Thank you, sir.
Okay, till then, Shornabu Banerjee, please go ahead.
Sir, thank you for your talk. Like the things with the terms that you use, not quite familiar with those. So where can I find them?
So for example, if any book on functional analysis would somewhere you can find. So for example, I can recommend the book by Bibi Limai. He has written a book called Functional Analysis for engineers or something like that. You can find it there. Or the book that I really like is by John Conway, Functional Analysis. So any of these 2 books should be very, very accessible.
Sir, and like for the projects will be given to us, right?
Yeah. So basically, we cannot go to the projects very, very like early in the course, because we still need to cover some ground. So maybe after the first month, it would be a right time to go to the projects, and then I will tell exactly what to do, how to do it, and so on.
Okay. Sir.
I mean, the book I will follow for the course is by G. Murphy. It's called C-star Algebras.
Okay, sir.
C-star Algebras and Operator Theory. That's the book's name. So if you want, so for example, this book, if you look at this book of chapter 1, then there is Hilbert space, inner products, completion, and so on, orthonormal basis, everything is there. So you can look at that as well.
Okay, sir. Thank you, sir.
Okay, so Shankar Shukla was asking that I'm acquainted with linear algebra and topology. What books can I refer to know more about C-star algebra?
Yes, the book by G. Murphy is exactly the book that I want to recommend. Yeah. And then August has a question. Yeah, I meant the principles of mathematical analysis, not the real and complex one. The first one, the baby Rudin.
Right. Any other questions? Anyone? Okay. So the next thing is that we are about to start a research project on it. So we will send you the respective form. If you are interested, then you just let us know. We will start the research project around in the middle of August, right? And it will continue for almost 2 months. So keeping that in mind, so we'll do the needful shortly. All right. Thank you everyone for joining this session. Thank you, Dr. Tathwamasi. for
Thank you
this session.
so much. And have a great evening. Take care.
Right. Thank you, sir. Goodbye.
Bye.